There are many different ways in which we can either measure or estimate a patient's cardiac output. They all have their own inherent flaws, but the one that's touted as the gold standard would be the Fick method, which we'll discuss here. Alright you guys, welcome back to another video lesson from ICU Advantage. My name is Eddie Watson, and my goal is to give you guys the confidence to succeed in the ICU by making these complex critical care subjects easy to understand. I truly hope that I'm able to do just that, and if I am, I do invite you to subscribe to the channel down below. When you do, make sure you hit that bell icon and select all notifications so you never miss out when I release a new lesson. As always, the notes for this lesson as well as all the previous videos are available exclusively to the YouTube and Patreon members. You can find links to join both of those down in the lesson description below. Also, don't forget to head over to ICUadvantage.com or follow that link down in the lesson description to take a quiz on this lesson, test your knowledge while also being entered into a weekly gift card. As well as don't forget that you can help support this channel through the purchase of an ICU Advantage sticker. Again, those are found at the website ICUadvantage.com/support, link down in the description. The Fick method is just one of many tools that we have at our disposal at the bedside to try and gain a better understanding or a clinical picture of what's going on with our patients. This method allows us to get a value of our patient's cardiac output relatively easily. So what is cardiac output? I'm not going to go over this in depth here. If you want to learn more about it, I'll link to a lesson up above where I cover just that. But essentially, our cardiac output is the amount of blood that's ejected by our heart per minute. Now, a normal cardiac output is 4 to 8 liters per minute. Now, fundamentally, we know that we can get this measure if we know how much blood the heart ejects with each beat, and if we know how many times per minute it's beating. Therefore, we can also say cardiac output is equal to our stroke volume times heart rate, where the stroke volume is how much blood the heart ejects, and then the heart rate is obviously how many times it beats in a minute. Now, a normal stroke volume is about 65 to 80 milliliters, and a normal heart rate is 60 to 100 beats per minute. Therefore, on the low end, if we take a stroke volume of 65 and a heart rate of 60 and multiply them together, we get 3,900 mLs per minute, or 3.9 liters per minute. And on the high end, if we take 80 mLs for a stroke volume and 100 beats per minute, we get 8,000 mLs per minute, or 8 liters per minute. Thus, our normal 4 to 8 liters per minute of cardiac output. Now, this is the physiologically expected result for cardiac output. The problem with using this to determine our patient's cardiac output is that we need to know their stroke volume. Now, we have many ways to get this, but they either aren't easily obtainable or aren't accurate. Knowing this, we need to have another way to determine cardiac output that's more easily obtained. Enter the Fick Principle. Now, you're probably wondering, what the heck is this Fick that you keep talking about? Well, essentially, it was developed by a German physician and physicist named Adolf Fick, who first mentioned of it in 1870 after studying cardiac output in dogs. The basics of the principle state that we can measure the blood flow to an organ if we know three things: the amount of oxygen taken up by the organ over time, the concentration of oxygen in arterial blood supplying the organ, and the concentration of oxygen in the venous blood leaving the organ. In our case, the organ that we're referring to is the body. So to put all this in terms that make a little more sense in the context of caring for patients in the ICU, we can determine our patient's blood flow, aka cardiac output, if we know three things. One, how much oxygen our patients are consuming. This would be their VO2. Two, the concentration of arterial oxygen, or CaO2. And three, the concentration of venous oxygen, also known as our CVO2. Now, we'll discuss this more in a minute, but hopefully you can see how these are all things that we might be able to easily determine. All this said, we actually can use other measures such as CO2, but O2, oxygen, is definitely the most common application here. In fact, Adolf Fick, when he was talking about the Fick Principle, actually just talked about some sort of marker that was being uptake by the organ. So, like I said, most practically, we're going to be using oxygen here. So, knowing everything at this point, we can actually discuss the actual calculation that we use to determine cardiac output using the Fick Principle. And that calculation is going to be cardiac output is equal to VO2 divided by our Ca minus Cv. So again, we know our VO2 is going to be our patient's oxygen consumption. And then our Ca is just shorthand for the concentration of arterial oxygen, and Cv is the concentration of venous oxygen. And then the Ca minus Cv is something that we know as the arteriovenous oxygen content difference. So I've given you the equation for the calculation, but how do you know that this actually works? Let's break things down a little bit. It really all starts with the oxygen consumption equation. And this is our equation for figuring out our patient's oxygen consumption, or their VO2. Now this equation is going to be our VO2 is equal to our cardiac output times the concentration of arterial oxygen minus the cardiac output times the concentration of venous oxygen. So if we think about this, our patient's oxygen consumption is equal to the difference between the amount of oxygen delivered and then the amount of oxygen that is taken away. What's left is how much was consumed by that organ or by our patient. Now, we determine the amount of oxygen that's delivered if we know how much blood is delivered, aka cardiac output, and what the concentration of the oxygen is in the blood, the Ca. And then we determine our concentration of arterial oxygen knowing two values with the equation of our Ca equals our saturation of arterial oxygen times our hemoglobin times 1.34. So the SaO2 is something which we can obtain from an arterial blood gas, or ABG. Our hemoglobin is something that we can get from either an H&H or a CBC. And then 1.34 is a constant that we use that basically is how much oxygen is bound per gram of hemoglobin. So essentially what we're looking at here is how much hemoglobin they have, and then how saturated that hemoglobin is, multiplied by our constant, and this tells us how concentrated the oxygen is in that blood, and then when we multiply that by our cardiac output, it tells us over time how much oxygen is being delivered, based on how concentrated that blood is with oxygen. Now we then can determine how much oxygen is left in the blood, again, also knowing the patient's cardiac output, and then using the same equation, just substituting the saturation of mixed venous oxygen, or our SVO2. So here we'd have our Cv is equal to our SVO2 times our hemoglobin times 1.34. Now, I'll discuss some adaptations here in a minute, but for our most accurate measure, we do need a mixed venous gas, which would require sampling blood from the pulmonary artery with a PA catheter. And so the amount of oxygen that's left in venous blood really varies depending on the organ that was supplied. Some organs use much more oxygen than others, and thus would have much less oxygen left in the venous blood. Now, in order to balance out all of these differences across all the different organs, we need to sample blood once it has all come together and mixed, and this is done by sampling from the pulmonary artery right before the deoxygenated blood gets to the lungs. Alright, so at this point it probably feels like you're back in math class again. I've thrown a lot of equations at you, and you might be wondering what's the point of talking about all of these different equations. Well, really, if we do some last bit of basic algebra, we can shift this equation for oxygen demand around and solve for an unknown cardiac output, assuming that we do know the patient's oxygen demand, their VO2, their concentration of arterial oxygen, and their concentration of venous oxygen. Then we end up with a new equation that is cardiac output equals VO2 divided by Ca minus Cv, just like we discussed. So the whole point of that was to give you guys an understanding of why it is that this equation tells us cardiac output. And hopefully you guys can see that and understand how we get to knowing that this will give us that value. Okay, so now that we've discussed all that, and hopefully you now understand how this works and that we can trust in the answer, let's talk about how we actually get these measures. So this brings us to the discussion of direct versus indirect Fick calculations. Alright, so the direct Fick is what's actually considered to be the gold standard. Interestingly though, that while it is considered the gold standard, it's almost never actually used due to the impracticality of it. To be the most accurate, the direct requires a direct measure of oxygen consumption, And to do this, we would measure how much oxygen was inhaled and then measure how much oxygen was exhaled, collecting this via a Douglas bag or some other collection method. And then doing this, we would subtract how much oxygen was exhaled from how much was inhaled, and then we would directly know how much oxygen was consumed. We also then want to sample blood for our CA and our CV that are the most representative. As I just mentioned, the CVO2 is best determined by sampling from the pulmonary artery. In reality, the best place to sample our CaO2 would be from the left atrium, just as all the pulmonary veins had come together and the now oxygenated blood has all mixed, but before it's gone on to any tissue for extraction. Now, as you can imagine, to get each of these direct measures requires a bit of skill, special equipment, and coordination, often which isn't going to be possible, especially for hospitalized patients and especially those in the ICU. So if we're stating that there's a direct measure, then this must imply that there's also some sort of indirect measure. So as I just mentioned, we often have difficulty obtaining the direct measure values required for that Fick calculation, thus we often substitute other values that are more easily obtained. Understanding, though, that by doing this, we're introducing inaccuracies into our measurements. Now, the Fick method was already determined to have about an 8% inaccuracy when looking at its comparison to actual measures of cardiac output. And then from there, each additional substitution we do is going to increase this error further. So it is important to understand this, as we often are weighing accuracy of values and measures for all sorts of things that we do in the ICU. Sometimes having a somewhat accurate value quickly can mean more for decision making and treatment than taking the time to get a more accurate value. So some of the common substitutions that we use are using a constant for oxygen consumption. So often we're just going to use 125 milliliters of oxygen per minute times body surface area. And this we would just plug in for our patient's VO2. Now this is reduced to 110 times body surface area if the patient is greater than 70 years old. And this was a constant that was determined by studies to be the average oxygen consumption of adults. Now we do also need to calculate a body surface area, which requires measuring a height and obtaining a weight measurement. Now another substitution that we do is using peripheral blood gas to determine our SaO2 and thus our concentration of arterial oxygen. Now this does introduce very little additional error, as it has actually been shown to be a pretty good surrogate for arterial blood concentrations. Another substitution is using a central venous blood gas instead of a mixed venous. So as mentioned, to get that true SVO2 to determine our concentration of venous oxygen, we need to have a PA catheter. Outside of a cardiac ICU, this really isn't common, but a central line is. And thus we can get an SCVO2, which, while not exactly the same as SVO2, is a pretty good surrogate for use in place. Now, one thing of note that even while we're using these substitutions, we want to make sure that our ABG and our VBG are being drawn together so that they are measurements of the difference of oxygen concentrations at the same time, as things can certainly vary and fluctuate. All right, so we went over quite a bit of information about how we do this calculation and how we get to this measure. So I do want to just quickly review the things that we are going to need to know in order to do this calculation. So we're going to need to know the patient's height. We're going to need to know the patient's weight. With these two things together, we can then calculate their body surface area. We also need to know their hemoglobin. We need to get an ABG for the saturation of arterial oxygen. We also need to get a VBG, either from a central or PA, for either the SCVO2 or the SVO2. And then we just plug these numbers into a calculator or do the hand calculation for it. Now, some monitors and some charting systems actually have this calculation built into them. You can also find calculators online, and they have apps for these as well. Otherwise, the hand calculation is as follows. And so remember, our starting calculation is cardiac output is equal to our VO2 divided by our CA minus our CV. So knowing some of the common substitutions that we do, we can then write this out as cardiac output is equal to 125 times body surface area divided by our SaO2 minus our SVO2 together multiplied by hemoglobin multiplied by 1.34 and then finally divided by 10. Now, that last division of 10 is really to get our answer from deciliters to liters for our final cardiac output. All right, so let's run through a couple of examples real quickly and hopefully help to cement this calculation for you. So for our first example, let's say we've got a 50-year-old male. His height is 5'10", he has a weight of 90 kilos, his hemoglobin is 13, his SaO2 is 99%, his ScVO2 is 70%. So first we need to calculate the body surface area using 70 inches and 90 kilos, and we get 2.08 meters squared. Now we can plug in our values. So on the top we have 125 times our body surface area of 2.08 divided by our SaO2 of 99 minus our ScVO2 of 70. After doing that, we'll multiply by our hemoglobin of 13 times 1.34 and then divide all of that by 10. So here we get 260 on the top divided by, the difference here is 29 times 13 times 1.34 divided by 10. If we solve for the bottom, we get 260 divided by 50.518, which then doing the math here gives us a cardiac output of 5.2 liters per minute. Simple enough, right? All right, let's do another example. So here we have a 75-year-old female. Her height is 5'4", her weight is 65 kilos, she has a hemoglobin of 16, an SaO2 of 96, and ScVO2 of 61. So first we again need the body surface area using 64 inches and 65 kilos. We get 1.70 meters squared. Now we can plug in our values. So here, remember that she's greater than 70 years old, so we're going to use 110. So we do our cardiac output is equal to 110 times our body surface area of 1.7. Divide this by first subtracting the difference of our SaO2 of 96 minus our ScVO2 of 61. Then multiplying by our hemoglobin of 16 times 1.34, and again dividing by 10. So here we get 187 on the top, divided by, the difference is 35 times 16 times 1.34 divided by 10. Doing this math gives us 187 over 75.04, and thus our cardiac output is equal to 2.5 liters per minute. And then knowing our body surface area, we can actually figure out our cardiac index if we take our cardiac output and divide it by our BSA. And this here we do 2.5 divided by our BSA of 1.7 gives us a cardiac index of 1.5 liters per minute per meter squared, which is definitely not good. All right, so now that you understand how it is that the Fick method works, how we get our measure for the calculation, and hopefully have a better grasp of it after doing a couple examples, we need to discuss some of the pitfalls. So not unlike just about every other measure for cardiac output, there are some pitfalls to be aware of that will impact the accuracy of this measurement. We already discussed some of those when it comes to our direct versus indirect measures and those substitutions. Also, in order for this calculation to work, there's the assumption that the systemic blood flow is equal to the pulmonary blood flow, and thus the left and right ventricles are equal in output. Thus, we'll actually see inaccuracies in pulmonary hypertension as well as heart failure. Also, intracardiac shunts can lead to mixing of blood, leading to inaccuracies in our determinations of our concentration of arterial oxygen and our concentration of venous oxygen. And then in patients that have a low Ca-Cv differences, so those that have high cardiac output states are going to lead to inaccuracies as well. And finally, if we use the average oxygen consumption in patients with either hyper or hypodynamic consumption, we're also not going to have an accurate measure. So examples here for hyperdynamic would be febrile patients, the tachycardic patients, even patients with pneumonia and sepsis, as well as on the opposite end, if we have patients who are hypothermic, as well as paralysis, are going to skew things the other direction. So just remember, if we have any of these, as well as if we're doing any of those substitutions, we need to understand that there's going to be some inherent accuracies with this measurement. And hopefully that all makes a little bit more sense now with the Fick principle and how we do this to do our calculations for cardiac output. And I'll actually link to some studies down in the descriptions below. But it seems like overall that the determination using this calculation in patients that accurately meet the criteria, that it is a pretty good measure, especially when we're comparing it to things like thermodilution cardiac output. that it's definitely a number that we can rely on, and you certainly may come across this in a lot of scenarios. So I hope that you guys found this information useful. If you did, please leave me a like on the video down below. It really helps YouTube know to show this video to other people out there, as well as leave me a comment down below. I love reading the comments that you guys leave, and I try to respond to as many people as I can. Make sure you subscribe to this channel if you haven't already, and a special shout out to the awesome YouTube and Patreon members out there. The support that you're willing to show me and this channel is truly appreciated, so thank you guys so very much. If you'd be interested in showing additional support for this channel, you can find links to both the YouTube and Patreon membership down below. Head on over there and check out some of the perks that you guys get for doing just that, as well as check out some of the links to other nursing gear, as well as some awesome t-shirt designs I have down there as well. Make sure you guys stay tuned for the next lesson that I release. Otherwise, in the meantime, here's a couple awesome lessons I'm going to link to right here. As always, thank you guys so much for watching. Have a great day.